Today we're going to conclude section 2.3. Last time we had talked about what the product rule and the quotient rule both looked like. I talked about most of what I wanted to say basically about the product rule, showed why what we would wish were true wasn't going to work with an example, and how the product rule itself gives us the right solution for that particular example. And we talked about how, I showed an example of how the quotient rule, as we wish it would be, doesn't work. And I had given you the definition of the quotient rule, but we hadn't gotten any further than that. So if you'll remember, this is where we were on our quotient rule. We had written down, actually, I guess I did. I had forgotten then, I guess, that I but I verified for you that it worked for our example. So this was our quotient rule. But we haven't done any examples on that except for this one that was very simple and cleaned up very beautifully. And so, of course, the whole purpose of having the product and the quotient rule is to work with the ones that don't clean up and don't work out very nicely in any other way. So we're going to do some examples then of the quotient rule. And one thing I'd like to draw your attention to is that the numerator of the quotient rule is very similar to the product rule. It's got all the same pieces. The only difference is actually the plus sign in the middle. Now, I structure it. I think it's ordered differently, right? So if you notice, it is actually the denominator and the derivative of the numerator, not the other way around. So you can't just switch these. Sometimes I have students who want to do this in the opposite order. You can't do that here because it is subtraction. But the reality over here on the product rule is that you could, in fact, do that here, and it would be okay because it's addition. So just kind of an awareness factor that the order really does matter in the numerator on the quotient rule. If you switch it around, you're going to get the wrong signs. So let's take a look then at an example for using the quotient rule. So on this one, there's no algebra to simplify and clean things up nicely. And the reason that there's not, just as a reminder, is because there's addition and subtraction in the denominator. Anytime you don't have a single term in the denominator, you can't simplify it and then move on from there. You're kind of stuck with what you have. So when we're using the quotient rule on this, we want to remember, in fact, I'll rewrite it on the screen just so that we have it on the screen. So we have it written as g of x times f prime of x. Yeah, that's fine. Oh, I told you last time, actually, too, that I would show you a mnemonic device. I think I said that. And then I didn't have time to do it, and so I mentioned I would do it this time. So there's a couple of mnemonic devices that I have seen used for the quotient rule. So let me do that first before we actually use it. Some mnemonic devices call this high and low, right? High for numerator, low for denominator. And so it's low, d high, minus high, d low, all over low, low. I know all of our brains work a little bit differently. For some of us, those kinds of mnemonic devices are helpful. If you're looking at that and you're like, that's stupid, that's not going to help me, then just discard what I've said. That's fine. That's not the one that I learned when I was taking calculus for the first time, but it's very similar. The one that I learned actually used, hang on, that wasn't what I meant to do. It used high over ho. And the reason it did is because it puts it together in a funny fashion. So let me show you what happens. So if you do the same thing here, and you say that you've got ho-de high minus high-de ho, all over ho-ho. Like Santa Claus, right? So that's the one that I learned, actually. And so honestly, even to this day, 20 plus years, well, we're getting really close to almost 30 at this point, 30 years almost, since I took calculus for the first time. This is how I think about every single time when I do a quotient rule. That's the power of mnemonic devices for some people, and then it is for me. Also, not only do you have, Santa Claus on bottom, but does anybody know where this expression is used? You probably would have seen it on Netflix, or Amazon Prime, or one of those kinds of things. That's where my kids have seen it at this point, because it is not a current sitcom. Has anybody ever watched Home Improvement? Mm-hmm. That's what Wilson says over the fence. He says, "Heidi ho," to Tim, the toolman Taylor. So anyway, fun facts from my childhood for you. There we go. Whatever it is that you use or think about in order to make sense of this, you start with rewriting the denominator. So it is the denominator, 5t minus 3. We are finding g prime of t. And then you multiply it by the derivative of the numerator. So what is the derivative of t squared minus 4? 2t. Anytime we're dealing with the quotient rule, it's subtraction in the numerator, and then we do it in the opposite order. So I use the numerator as my first piece, t squared minus plus 4, times the derivative of the denominator. What's the derivative of this denominator? It is 5. Okay. And then we need to write that over the denominator squared, 5t minus 3 squared. Already even this semester, I have seen, I'm going to do something on the screen that is absolutely incorrect, so please don't copy what I'm about to do. Just pause for a second, because I want to remind you why it doesn't work. You can't cancel this piece with one of these down here. All right? So I've seen that happen a couple of times already. Just a reminder, the reason you can't is because it's missing from this piece over here. If all three of the pieces that were separated with addition and subtraction had the 5t minus 3 in it, we'd be good to go and we could do that, but they don't. So there's no simplifying like that I can do on this problem. But what I can do is I can clean up the numerator and see if maybe it has a factor of 5t minus 3. It can't because both pieces don't, but just to be aware, I do need to simplify and clean up the numerator on this one. So I will distribute like so. So 5t times 2t would be 10t squared, and then negative 6t. And then I need to distribute this 5, but also a negative, so in some sense you're really distributing like a negative 5 through that parenthesis. So you're going to have negative 5t squared and negative 20. Any questions about the simplification? Not sure where something came from or anything like that. Okay, combining like terms, what do you see that would combine in the numerator? Yep, 10t squared and negative 5t squared, so I would get 5t squared, right? And then the other two pieces don't combine, so I have minus 6t minus 20. I mentioned before, I know for a fact that these cannot simplify. That is to say, it might factor. I mean, like that's a possibility, but it won't factor into something I can simplify with the denominator. The reason that I know it will not be able to be done is because this original numerator piece right here did not have a factor of 5t minus 3. 5t minus 3 in it. So I'm not going to be able to find a way to factor the numerator still into having a 5t minus 3 because both pieces didn't have that to begin with. So our final answer is where we are at the bottom now. G prime of t equals 5t squared minus 6t minus 20. There's another way that you can know it doesn't factor. Just an awareness. I do have a 5t squared here, so if I tried to factor it, the beginning of one of my parentheses would have a 5t, right? And that matches here. The problem is that 20 doesn't have a factor of 3, right? I can't take 20 and make it a 3 times something equals 20, so there's no way for that to be able to happen. So another way to check and make sure that you cannot in fact simplify. Let's try another one. This one has some trig involved, and I know for some reason when we look at trig we get a little bit anxious, but trig with derivatives is always really, really nice because it has those nice forms, right? Sine is the derivative of sine is cosine, the derivative of cosine is negative sine. So when we're looking at this one right here, if I take the denominator, it's x cubed. What's the derivative of sine x in the numerator? Cosine of x. Minus, and now I want the numerator, which is sine of x, times the derivative of the denominator. What's the derivative of x cubed? 3x squared. I'm going to write that sine x in parentheses just because I don't want you to think that you can combine the 3x squared with the x that's inside of the sine, just because they're sort of beside each other. So I'm just going to distinguish it that way to remind us. And then it's over x cubed. Now, this problem can be simplified with the denominator. And the reason it can is because this x cubed has components of it that appear in each of the three pieces, the denominator and each of the two pieces that are separated by subtraction in the numerator. Yes, ma'am?
X cubed squared.
Would what be x cubed squared? Oh, yes, I missed it. Thank you. You're right. Let me do this first then. Yep. Okay, this is what I wanted to do. Thank you. Yep. Denominator squared. Thank you. All right, so all of these pieces have at least two x's in them, right? The first piece has x cubed, the second piece has x squared, and the denominator has actually x to the 6, like you pointed out. So we're going to be able to reduce the sum of those x's out. In particular, 2 of those x's out. So 2 of these are going to cancel out, going to leave me with, leave me with x to the first here. 2 of these are going to cancel out completely, right? And then down here, I haven't written it out yet, but this is x to the 6th, and 2 of these are going to cancel out, leaving me with an x to the 4th. So some of these pieces are going to actually eliminate one another. So I am going to have a cosine of x here, x cosine of x here. I still have the sine x and I still have the 3. It's a little bit more natural to write the 3 before the sine x. So I'm going to rewrite it as minus 3 sine x. And then it would be over x to the 4th. Any questions on that one? Okay, so back in section 2.2, we talked about the derivatives of sines and cosines, and I told you that we would see the derivatives of the rest of the trig functions soon, and soon is today. So these are our other 4 trig functions, and hopefully you'll see pretty quickly why it is that we would not consider them maybe simple derivative rules. They're a little bit messier. So the derivative of tangent is secant squared of x. The derivative of cotangent is negative cosecant squared of x. The derivative of secant x is secant x tangent x. And the derivative of cosecant x is negative cosecant x cotangent x. Okay, so I always like to throw out things that help me to remember, and I'm fully aware that that doesn't necessarily make it something that would be useful to you, but for some of you it might. I like patterns. Patterns help me to remember things. So like when I have a brother-in-law who is really into patterns, so he has like the alarm on his house, and he doesn't know what the alarm on his house is. He just knows the location of the buttons. That's how his mind thinks about things, is location-wise. It's very spatial reasoning. Well, for me, patterns is something that really helps me. So take a look real quick. I'm going to write the other 2 that we have on here just so that you can remember and see the pattern that I'm trying to establish. Before we did the derivative of sine was cosine, right? And then that's an x. And then the derivative of cosine was negative sine. So one of the common mistakes that people make when they're dealing with trig functions is remembering which ones become negative. And if you take a look, the ones that become negative are all the co-functions. Do you see them? Every co-function, cosine, cotangent, cosecant, all has a derivative that's negative. And if it's not a co-function, its derivative is not negative. So that's something that helps me because I see that pattern. The other pattern that's really nice is kind of this grouping, the way that they're set up. These 2 seem to go together, right? They seem relatable because they oscillate between one another. These 2 seem to go together because I have them showing up with squares. Secant squared, cosecant squared. And not only that, but the tangent becomes secant, while the cotangent becomes cosecant. So there's a nice pattern relationship that's there. And then the other 2 have the same sort of thing. The secant becomes secant tangent, and the cosecant becomes cosecant cotangent. So those are some ways that help me to remember which one does what. You absolutely have to memorize these, and you don't have a whole lot of time to do it. You're going to be doing a gateway for me on Friday. And on Friday, some of these are going to show up on the gateway, and you need to know which one's which. You don't have any devices or you won't be able to use your calculator. There's no simplifying needed or anything like that. You will use a pencil and that's it. So you need to remember which one's which when you take that quiz. If for some reason that's not quite down, you have opportunities, of course, to make things up later. But the advantage for you, there's 2 advantages. Passing it the first day, passing means that you get 18, 19, or 20 correct out of 20. The 2 advantages, the first advantage is you don't have to come and retake it. And that's an advantage because your time's worth that. It's worth something, right? It's worth something. The second advantage is you get extra credit. Speaking of extra credit, did you guys get my email about extra credit for math club stuff? Fantastic. Check your email if you didn't. I sent a math email through Canvas, so it should have appeared there. There's a math club meeting tomorrow, and there's 3 more, I think, through the year. Maybe there's I think there's four total through the semester, maybe 3. Anyway, opportunities for extra credit if you would like to come to those. I know that doesn't always work for everyone, but if you're interested, they're a lot of fun. Do some interesting things. One of the things we get to do is watch a movie. So that's pretty cool that you get to come watch a movie and get extra credit for it. Anyway, I'll let you check your email out for that. But the first time that you take this quiz, if you pass it, get an 18, 19, or 20 the first time, you get 5 points extra credit, okay? So it's good stuff there. So let's do some examples here with derivatives that involve those new trig functions. So the first one we have is 1 over x minus 12 secant of x. And I'd like to remind you that we don't have anything, well, it's not true now at this point. We do have something that we could deal with the 1 over x, and we could use the quotient rule. We could. It would be way overkill and so not necessary. And the reason is because 1 over x can be rewritten as x to the negative 1, and you can use a power rule. So if you can use a simple rule, a power rule, it's usually a lot easier to work with than using more powerful and an unnecessary, in this case, rule, the quotient rule. So if I have x to the negative 1 minus 12 secant of x, just that's a rewriting step, then I can take my derivative pretty nicely. What's the derivative of x to the negative 1? Yep, negative x to the negative second. Good stuff. And what's the derivative of negative 12 secant? Well, the negative 12 is a constant multiplier, so it stays. And what does our new rule say that the derivative of secant is? Secant x, tangent x. And please remember, while sometimes I sort of shorthand what I'm saying out loud and I just say secant, it's always got to have an angle next to it. If it doesn't have an angle next to it, it has absolutely no meaning. It's like saying square root. You're like, well, square root of what? Right? It doesn't mean anything if I don't have something underneath the square root. Same thing here. It has to have an angle next to it, and the angle in this case is x. The only thing that I would need to do here is to rewrite the x to the negative 2 the way it was originally written, which was originally written in the denominator. So this would be negative 1 over x squared. And then I would have minus my 12 secant x tangent x. Any questions on that one? Okay. The next one's a very, looks very clean and simple. I've got sines and cosines. We've dealt with sines and cosines before, no problem. But what do you notice about these that's different than what we have done thus far? They're what?
They're together.
They're together. In particular, they're together with what operation? Multiplication. These are multiplied together. So because they're multiplied together, this is a product rule. Okay, there are two pieces. They are multiplied. I have to use the product rule. So in using the product rule says I simply rewrite the first piece, sine x. And then I need the derivative of cosine of x. So what's the derivative of cosine of x? Negative sine of x. Because it's a product rule, it's addition. And then I'm going to do the opposite, right? Now I need the derivative of the first piece, sine of x. So what's the derivative of sine x? Cosine x. And I rewrite the second piece, which is also a cosine of x. So taking a look at this then, I have negative sine squared of x plus cosine squared of x. So if you'll remember from trig, when we square sines and square cosines, we put the square in between the sine and the angle, because if we put the square after the x, it looks like the angle is what's being squared. So it's just a distinguishing feature that we use for trig functions only. The squared goes next to the word sine or next to the word cosine, okay? This looks a lot like a trig identity you have. It's not. The trig identity that feels very much like is sine squared plus cosine squared equals 1, but one of these is negative and the other one's positive, so it's not that identity. So there isn't anything else that can be done to simplify or clean this up, or at least nothing that would be expected. It actually is another identity, but not one that we would need to work with in calculus. So we stop at this point. Any questions on that? All right, let's try one more. This one is 2 minus 3x. Oh, I had an error in my notes. Over tangent of x. So this one's a quotient rule, right? Yeah, got a quotient rule here. So the quotient rule says the first thing I'm going to do is I'm going to rewrite the denominator, tangent of x. And the next thing I'm going to do the derivative of the numerator. So what's the derivative of 2 minus 3x? Negative 3. That's right. Quotient rules are subtraction. And now I rewrite the first piece, the numerator piece, 2 minus 3x. And I need the derivative of tangent of x. So what is the derivative of tangent of x? Right, it's secant squared of x. And then what is my denominator when I'm working with the quotient rule? It's the original denominator squared, right? So my original denominator was tangent of x, and now I have it squared. All right, the only thing that we're going to need to do to clean this up is to distribute the secant through this, all right, because we've got the parentheses that are associated there with a subtraction between those two terms. So I'm going to move a few things around too. For example, tangent of x times negative 3. It's more natural, right, that you write the negative 3 first, so negative 3 tangent of x. And then I have this negative as well that's getting distributed, so all my signs are changing as well as multiplying by secant squared. So I actually have negative 2 secant squared of x. And then I have positive 3x secant squared of x. And it's all over the tangent of x squared. Or if you prefer, I could have written it this way. That's probably a more natural, based on what I was telling you before. You could do tangent squared of x like that. All right, any other pieces that maybe you wanted to, and I put g of x, that is so g prime. Make sure you fix that since mine did not have my prime on there. I moved on too quickly. Okay, so it's g prime of x. Okay, last example for this section looks like this. So it kind of looks like there's multiplication in the numerator and there is a denominator as well. So this is one of those cases where it's not really multiplication in the numerator, right? It's just 3 that's being multiplied by something. So it's probably just as well if you go ahead and distribute this at the beginning. Whoops, that's not my button I needed. Distribute this at the beginning, just so that you're not looking at it like it really has multiplication effect, right? It's really just 3 minus 3 sine x over 2 cosine x. All right, so let's take a look then at the derivative k prime of x. Somebody tell me what I'm going to write down first. 2 cosine x. So the denominator gets written down first. Okay, somebody else tell me the next piece that I would write down. Exactly, the derivative of the numerator. And what is the derivative of the numerator for this function?
Negative 3 cosine x.
Good job. Negative 3 cosine of x. Okay, it's a subtraction sign next. So somebody help me. What's my next piece? The numerator. 3 minus 3 sine x. Okay, new person who hasn't spoken, tell me something else. What am I going to write after 3 minus 3 sine x?
G prime.
Yeah, so I need the derivative of the denominator, right? So what's the derivative of the denominator, Reed? Do you know?
Is it negative 2 sine of x?
Yes, it is. Good job. Negative 2 sine of x. Okay? And my denominator, what will it be? Right, it's the 2 cosine of x squared, and I do have to square both the 2 and the cosine on that denominator. So let's figure out what we have here cleaned up a little bit. The first pieces that are being multiplied don't have any addition or subtraction, so I can just combine the like terms that are there. So this is negative 6 cosine squared of x. The second piece over here actually has pieces that can be distributed and cleaned up. I also take a look here, notice that I've got a negative here and a negative that I'm distributing here. So those are going to cancel out. So let's kind of note that sign change there as well. And we'll distribute. So now I have 2 times the 3, so this is 6 sine x. And then I have minus 6 sine squared of x. And this is all over 4 cosine squared of x. Is everybody good so far? I mentioned a trig identity a moment ago as being something that is useful when it shows up. And the trig identity that I mentioned was that sine squared of x plus cosine squared of x equals 1. It's called a Pythagorean identity. There's 3 Pythagorean identities, but this is the one that we tend to see most often come up. And it's actually here in our problem. Take a look. I realize that they both have a -6 next to them, but that's actually what makes this work. If I were to put these 2 items together and factor out the -6 just from those 2 items, I would have -6, and then I'd have cosine squared x plus sine squared x, and then I'd have the other piece in the problem plus 6 sine of x, all over my 4 cosine squared of x. So when this identity shows up in a problem, I expect you to be able to see it and use it. It doesn't occur all that frequently, but it will occur occasionally. So this piece right here then is equal to 1, multiplied by the -6 that's before it. So it's just -6 plus my 6 sine of x over 4 cosine squared of x. There's exactly one more thing I can do. Does anybody see it?
Can you take it 2 out?
You can. Each of those numbers that are there are even, right? The 6s and the 2s, or the 6s and the 4s. So yes, you can factor out or cancel out a 2 of each of them. So these will each become a 3, and this will become a 2. So your final answer for k of, was it k of x? Yeah, k of prime of x would be, and I've got a little bit of space problems going on here, would be -3 plus 3 sine of x over 2 cosine squared of x.